Hello and welcome to this video. I'm Vignesh Viswanathan, a PhD student at the University of Massachusetts Amherst, and in this video, I'll be talking about a recent EC paper on a general framework for fair allocation under Matroid rank valuations. This is joint work with my advisor, Yair, Zick, who's also at the University of Massachusetts Amherst. This paper presents a broad framework for fair allocation, but under the specific assumption that agents have Matroid rank valuation, the specific class of valuations that I will go into in a little bit. So before I go into all of that, let me first describe the basic problem. We have M indivisible goods G, and we have a set of n agents with differing preferences over these goods. And these differing preferences are captured using a valuation function. That is, each agent I has a valuation function Vi, which maps each bundle of goods to a positive real value or a non-negative real valued number, which denotes the value that that bundle of goods provides to that agent. Now, our goal in this setting is to compute an allocation of these goods. That is, we want to divide the set of M goods into n plus one sets, or partition the set of M goods into n plus one sets, such like this will be denoted by tuple X, which goes from X0 to Xn, where each agent I is receives the bundle Xi, and X0 consists of the unallocated goods. Essentially, we're dividing the goods up and giving an agent some bundle of goods and don't want to allocate each good twice. That's all that's saying. And an important definition that I'll keep using throughout this presentation is the definition of utility. Utility is essentially like the utility of an agent I under the allocation X is essentially just the value they receive under that allocation. That is, it's the value Vi of Xi. It's fairly straightforward. On the right, we have a very simple example where just each agent receives some bundle of goods, and the green apple at the end of the allocation is at the green apple is unallocated, and so it is kind of allocated to X0 or is added to the bundle X0. Now, coming back to what I mentioned before, that we assume that each agent has Matroid rank valuations. And this is a special class of valuations characterized by two basic properties. The first is that Vi, that is the valuation function of any agent, is binary or has binary marginal gains. That is to say, if you take any good and add it to any bundle, the marginal value of adding that good to any bundle is either 0 or 1 according to the agent I. That is, they either like the good or they don't. It's a very simple, like 0 or 1 marginal gain model. The second is that each agent's valuation function is submodular. That is, it provides decreasing marginal returns to scale. Um, the exact definition says that if I were to take two sets, one which is a subset of another, and add the same good to both these sets, um, the marginal gain from adding the good to the smaller set must be at least as much as add the marginal good of adding the marginal gain of adding the good to the larger set. This is a very commonly used property in a lot of the economics literature. Now, this is not a commonly used class of valuation functions. Most of the fair allocation literature, in fact, looks at additive valuations or more general submodular valuation functions. However, we specifically choose this class of valuations to study because we are very motivated by the application of fair allocation to university course allocation. University course allocation, where essentially we allocate course seats to students, can be modeled as a straightforward fair allocation problem where the students correspond to the set of agents and each course seat corresponds to an item or to a good that we would like to allocate. However, the specific nature of university course allocation means it has certain unique requirements that are not otherwise required. For example, first is that because of the scale of the problem, we may not be able to elicit or even store cardinal preferences for each student for each class because there are way too many students and way too many classes. The second is that there are additional constraints which prevent each student's valuation from being additive. For example, if we're allocating course seats to students, there is no point of having two seats in a course uh, because, well, one's enough for one student. And similarly, there's time constraints, there's cardinality constraints. That is, universities usually have rules where you can't take more than 5 courses, more than 6 courses. And similarly, you can't take 2 courses that have an overlapping time slot. Uh, and finally, like as universities commonly do, students are prioritized differently. For example, a student closer to graduation is given a higher priority when choosing their courses. And maybe a freshman or a student who's taken much fewer credits is given a lower priority. At least I believe that's how it works at UMass. Now, this can be modeled like all of these constraints are satisfied by Matroid rank valuations or binary submodular valuations to a large extent. And this is the reason we studied this specific class of valuations to see what we can do there. It's also worth noting that looking at more general class of valuations means that like the problems like computing fair allocations in general becomes computationally intractable. And by assuming this simpler class of valuations, we prevent that. We can actually do a lot of things in polynomial time, which is really nice. Now, the main thing that differs our work from prior work is the way we approach this, or the way our main algorithm works. If you look at prior work, they usually like focus on one specific fairness objective or fairness metric. Of course, there are so many in the literature. For example, there are so many works, incredible pieces of work that look at maximizing Nash welfare. Similarly, on like ensuring NV freeness or EFX or EF1, and similarly Leximin, and the list goes on, right? There are so many different fairness objectives or justice criteria that you can optimize for in the fair allocation literature. What we do in this work, and this is really like the cool part of our work, is that we provide a reasonably simple algorithm to compute to compute allocations that satisfy almost all these justice criteria or fairness objectives. Obviously, not at the same time, because that would be impossible, but our algorithm allows you to choose which justice criteria you want to maximize, and then it simply does it, which is the main contribution of our work. And just to put this more formally, we define a justice criteria as simply a way of comparing allocations. That is, you want to look at two allocations and say that, oh, this one's better because this one's fairer, or this one's more efficient for whatever reasons that you have in mind. Like, for example, like say the Nash welfare, which is defined as the product of all agent utilities given any allocation. You can think of that as like simply a way of comparing allocations, right? Allocation X is better than allocation Y if allocation X has a greater Nash welfare than allocation Y. Similarly, you can like just this is essentially an abstraction of what a fairness objective is. You can extend this to max min share, like NV freeness, Leximin, and so on. Now, and the general goal here is to find an allocation that maximizes psi, the justice criterion that you input. This could be max Nash, this could be finding a max Nash welfare allocation, this could be finding an NV free allocation, this could be finding like a weighted Nash allocation, and so on and so forth. Now, before like the main contribution is our algorithmic framework, but before we do that, we feel like it's important to present like the motivation, like the inspiration for our algorithmic framework, so to speak, which is basically from a mechanism that comes from an episode of The Office. Essentially, they were trying to divide Christmas items, like Christmas presents, among the employees of the office, and follows a similar structure. So their mechanism is essentially like the round robin algorithm, where first all goods start off unallocated. That is, you see all these items under the Christmas tree. And then each agent gets a turn. For example, say the leftmost agent gets a turn, and they can pick an item from the set of unallocated items. That is, let's say they like this item and they pick it. Similarly, the next agent, like the turn passes, the next agent gets a chance to pick an item from the set of unallocated items that they like. However, like say we come to the rightmost agent and the rightmost agent does not see any unallocated item that they actually like. They don't really like any of the unallocated items. So what they can do is they can steal an item from another agent. This is the classic Christmas game, like White Christmas, I think. I keep forgetting. Where they steal an item from another agent, and the agent they stole from then gets a chance to steal an item from someone else. And finally, like this whole like transfer path, as we call it, ends when someone finally picks an item from the pool of unallocated items. And this is essentially this is the high level structure of our algorithm. Of course, like given like how these thefts work, it's going to be really hard to analyze it or even show any fairness guarantees when you can steal arbitrary items. However, we show that the only thing that you need to ensure when actually running this algorithmically to compute fair allocations is to ensure that agents can only steal goods in a nice way. That is, I can only steal a good from some other agent in my turn if that agent I'm stealing from can make up for the loss that they felt when I stole their item by stealing an item from someone else. That is all. Just ensure that people are nice about it and that they can make up utility by stealing other items, and we're golden. And the second thing is that you don't want infinite paths. So you want to say that an item can be stolen or moved around in a transfer path at most once. So once you make these two assumptions, like once you make the second assumption, rather, transfer paths only terminate at unallocated items. So that's it. That's the high level idea of our framework. Here is the broad pseudocode. And yes, it is that simple. So the algorithm, like I said, starts with all items initially unassigned. Then we just proceed in rounds. At each round, we pick an agent I greedily according to the justice criterion psi, whatever input justice criterion there is. That is, if you want to maximize Nash welfare, pick an agent such that giving them an item would increase Nash welfare the most. And then see if there is a transfer path, this nice transfer path from that agent to the set of unallocated items where they can steal an item from someone who can recover their utility by stealing an item from someone else, and so on. Now, if there is a path, awesome. Execute that transfer path, that is like transfer goods backwards along that path, and move on to the next agent. Otherwise, just pretend that I does not exist anymore. That is, remove I from your set of agents or remove I from play and continue the algorithm, right? That's the main algorithm. And finally, once you've either removed all the agents or you've run out of items to assign, you simply return whatever allocation you have built up so far. That's it. The one complicated step here is obviously like whether these transfer paths can be computed. And it turns out that you can compute them via a simple breadth first search, like over a straightforward graph. Please refer to the paper for more details. I don't think I'll have time to go over that right now. So this is the algorithm. I told you it works for like several different like justice criteria, but what I'm going to tell you next is exactly when it works. And it works when the justice criteria satisfies two basic properties. The first is Pareto dominance, right? Essentially, your justice criteria should respect Pareto dominance. That is, if I create an allocation X that Pareto dominates Y, then X must be better than Y according to the justice criteria psi. For those who are unclear about Pareto dominance, it essentially says that like each agent is better off under X than in Y, but one of the agents is strictly better off in X than in Y. So X is like it, there has been no harm done to any of the agents in X when you compare it to Y. Essentially, condition one says that the justice criterion needs to be consistent with Pareto dominance. That's reasonably straightforward and not an unreasonable condition to have. The second is a little more tricky. We call it the gain function condition. Let's say you have an allocation X, and let's say you have an allocation I, you have an allocation Y where the only difference between X and Y is that agent I, some agent's utility, differs by exactly one. That is, say the leftmost agent here is agent I. In X, they had a utility of 1. In Y, they have a utility of 2. Now, if we were to compare X and Y according to psi, so the gain function condition says that either psi of Y minus psi of X or psi of Y divided by psi of X must be a non-increasing function of the value of the utility of I under X. That is, the justice criterion must have some sort of concavity property. Now, this seems a little like it's not exactly trivial exactly why this is reasonable. So I'm going to give you a simple example of why, say, the Nash welfare objective satisfies these two properties, right? So let's look at the Nash welfare objective. Of course, it trivially satisfies the Pareto dominance condition, right? You Pareto dominate an allocation and the Nash welfare strictly improves. The second is if you look at like the ratio of two allocations, say X and Y that we were looking at before, where the only difference between X and Y is that some agent I's utility increased by 1, then you have this equation here where you just divide the product of utilities and all the terms cancel out except I's utility, so that gives you this nice expression here, which is like psi y of psi x is equal to vi of xi plus 1 over vi of xi. This is clearly a decreasing function over vi of xi. So this Nash welfare objective trivially satisfies, not trivially, but satisfies the two conditions we presented before and can be computed by general Yankee swap. Before I go into other metrics that can be computed by our algorithm, I should note that our gain function condition, that is the condition that we just looked at, was simplified for this presentation. Our algorithm actually works when the justice criteria satisfies a simpler or more general notion of this, more general version of this condition. We leave to you to look at the paper to find out more. Right. So now, what is our main result? Our main result is that for any justice criteria that satisfies the two conditions I presented before, that is the Pareto dominance condition and the gain function condition, the general Yankee swap algorithm, the only algorithm I talked to you about in this presentation, computes an allocation that is psi maximizing for the psi that satisfies the two conditions, and it is welfare maximizing. That is, it maximizes the total utilitarian social welfare, more formally defined as the sum of the utilities of each agent, which is really nice. And to add to that, this mechanism is strategy proof. That is, no agent has an incentive to actually misreport their preferences. That is to say, they don't have any incentive to lie and get a better outcome, which is a really good property to have, especially in course allocation, where you don't want people thinking about how they're trying to cheat the system to get a better outcome, which is great. Here are the other justice criteria that can be computed using general Yankee swap. You can compute leximin, weighted leximin, max-min share, weighted Nash welfare allocations, and actually there's some more stuff that can be computed as well. And I don't want to go over exactly why these gain functions work, but if you're following so far and are still curious, I would highly recommend checking out the paper to see exactly why they work. It's not, once you the most complex result is showing that only those two conditions, like Pareto dominance and gain function, were necessary. After that, showing that all of these justice criteria satisfy those two conditions are almost trivial. So would highly recommend like checking out the paper if you would like to know more. Now, of course, I've been going on and on about how many different justice criteria can be computed using our algorithm. I should also highlight that it doesn't work for every justice criteria there is. For example, a very popular notion of fairness is that of envy freeness, and specifically, our algorithm doesn't work for weighted envy free. Our algorithm cannot be used to compute weighted envy free allocations. Then the reason for that is simply that the notion of envy freeness itself does not satisfy Pareto dominance. That is, if the agent on the left here envies the agent on the right, say if this agent envies, if this agent envies this agent on the right, then this envy only increases when I Pareto dominate the allocation and give the agent on the right another good. That is, so unfortunately, envy does not satisfy Pareto dominance, and so our framework cannot fully work there. So yeah, that's been the presentation. Here are some basic takeaways. Our algorithm is cool and works on a lot of stuff. It's also fast and strategy proof. But the big question essentially remains, well, we assume binary submodular valuations in the beginning. What about generalizing it beyond that? It'd be really cool to show that this works on other classes of functions. We have done some work on this front. Uh, for example, we have worked on, well, instead of 0, 1 valuations, what if you had 1, 2 valuations? Then we show that, well, a similar framework works. Similarly, like for -1, 0, 1 valuations, again, a similar framework, but we're now looking at other forms like general submodule evaluations, ternary submodule evaluations, and so on. Keep you posted if we actually find something, but I'm very hopeful. Finally, I feel like this is also really cool that we are currently working with the UMass Registrar's Office to try and get this algorithm implemented. If you have any questions about that, please email Yair or me. Now, that's the end of my presentation. When I presented this at EC, I did receive a very interesting question about whether this algorithm is similar to the Edmonds path augmentation algorithm for Matroid union and intersection. And I feel like I should answer it here as well in case you have that question. And the answer to that is essentially yes, it is similar, but you can think of our algorithm as breaking open the black box of like the Edmonds path augmentation algorithm for Matroid union and adding a fairness constraint to it, like um, adding a line that says, well, decisions should be made in a fair way. And our result essentially says that this simple procedure works. So in that sense, like in terms of a theoretical sense as well, that is really cool. So thank you for listening. Feel free to email me or Yair if you have any questions. Thanks.